Wenhe and Xinyu's presentation of Machine Learning Funnel Project. The goal of our project is to design and compare several machine learning algorithms to detect diabetic retinopathy, which is DR in short. DR is a leading cause of blindness in the working-age population of the developed world. It is estimated to affect over 93 billion people. However, detecting DR is a time-consuming and manual process that requires a trained doctor to examine and evaluate the photographs. While this approach is effective, its resource demands are very high.
Therefore, the need for a comprehensive and automated method of DR screening has been recognized, and previous efforts have made good progress using image classification, pattern recognition, and machine learning. In this presentation, we will present you with several machine learning algorithms to identify whether a patient has DR, and if so, how serious his or her disease is. The input of the algorithm are the colorful photography of human's retina, and the output are labels that represents the state of illness.
The dataset we used was downloaded from Kagos.com, which composed of more than 5,000 images of patients' retinas, and each image is of the format 224 times 224 times 3. There are 5 categories, which also correspond to the 5 labels in our problems. And from no DR, mild, moderate, severe to proliferate DR, they are labeled as 0 to 4. Before starting our algorithm, we need to pre-process our dataset first. The label distribution was imbalanced here. The labels of no DR took a large part in our dataset, so we first dropped some data with no DR label to balance the distribution.
We know that the age and texture in retina are the most important factors to identify DR illness. Therefore, we apply Gaussian filter to do the age enhancement. For the data process pipeline, we first rebalance data by dropping some zero labels. Then we do edge enhancement to better collect features. And finally, we apply data normalization.
Okay, now let's come to the algorithms and solutions. In this project, we worked on 5 classification algorithms. The KNN and SVM algorithm are the baseline for the project. And we then continued to work on several CNN algorithms with the NET, ResNext with transfer learning, and we also developed a restrained ResNext. First, applied 2 simple classification algorithms as the baseline for our project. KNN is one of the most basic algorithms for classification. It does not have a specialized training phase and use all the data for the training while classification. In order to classify a data point, we first find out the k nearest point to it to compose its neighborhood. Then we assign the data to the class which appears most frequently in its neighborhood.
Apart from KNN, we also use SVM to do the classification baseline. The core idea of SVM is to find a hyperplane by using kernel mapping.
KNN algorithm achieved a record of 66% while a precision of 58%. SVM achieves a better prediction result compared with KNN, which both the record and precision were around 70%. Now we focus on the convolutional neural network. We first applied a simple LeNet architecture here, which contains 2 convolutional layers, 2 subsampling layers, and 2 fully connection layers. LeNet achieved a high accuracy of 95% on the training set, while only an accuracy of 70% on the test set. It had an overfitting problem and also took a long time to train. To increase the efficiency of the training process, for the next algorithm, we applied transfer learning on the ResNext. We additionally add 2 more fully connected layers to the ResNext. The weights inside the ResNext were frozen, and only 2 fully connected layers were subject to change.
In terms of architecture, this model introduces wide residual block, aka aggregated residual transformations, to edit the cardinality of networks. Besides, to avoid overfit, this model introduces dropout, which could randomly drop neurons in the model, and batch normalization, which could do normalization in each batch input. The ResNext compared with ResNight has the same structure but introduced aggregated residual transformations to enhance the cardinality. Overall, it contains similar parameters and even smaller size of parameters, but higher accuracy. The transfer learning achieved a better result on the test side compared with ResNight. However, it still yields a problem of overfitting. The overfitting helps us realize the problem of low test accuracy should be the dataset itself. In other words, the dataset is not large enough. To enhance the dataset, we apply data augmentation by using ImageAug, a library for data augmentation. Our augmentation includes flip, both horizontally and vertically, F-in, pixel dropout, apply mask, rotation, and saturation adjustment. For the solution, we realized that the feature that the pre-trained ResNext is sensitive might be different from our task. Therefore, we decided to retrain the network by allowing value updates for all convolutional layers. To avoid overfitting, we will apply data augmentation we mentioned in the previous sections, the training process. Our retrained ResNext achieves both higher training and testing accuracy, and both of them are around 80%. However, by applying strong data augmentation, we find the model is hard to converge. Besides, since we need to update all convolutional layers, the training process is quite time-consuming. Finally, we run the model on the whole site and calculate the precision and recall rate. And both of them are around 83%, which are pretty good compared with our baseline. Besides, we also draw confusion matrix in this plot. The darker color means a higher value. From it, we can tell that the mild is the label that hardest to identify. The table below is the recall and precision rate for all rhythm we propose. We can tell our retrained ResNext has the best results for both recall and precision rate. However, the transfer learning in this case does not work well. The possible reason should be the different target features that the model can extract and the task requires.
Finally, we applied some model compression techniques. We found that prune was very efficient in this project without the loss of precision. We applied 40% prune on the linear layers, and it turned out that the precision was only dropped by 0.1%. The quantization, however, though reduced the storage, also caused a less accurate result. It shows the trade-off between the storage and precision.
We further investigate what makes CN activate by inspecting the weight in convolutional layers and the weights in the corresponding sigmoid activation functions. This technique is also called CAM, class activation mapping. From the CAM, we can tell no DR and pro-life active DR have the exact region that activates the neural networks, while for the rest of the three labels, we can say the neural networks activates for nearly the whole graph, which suggests that some features are not fully learned by the neural networks. But there are some takeaways we got from our project. The first thing is about the data. So data is also important, and maybe data is the most important thing I would say that. Because if you have a really well-balanced data and you can get the features from data well, then you have a good result. And second thing is about adding the network capacity is not a panacea. In other words, either you are using a really fancy network structures or your network is really deep. If you do not have a really good data set and some really good pre-processing techniques, then you will not get a really good result. And thirdly, the overdose data augmentation may slow down the convergence. It's kind of like an experiment result we got from our project.